Okay. Oh, we have to clear this up. Okay, so I think we'll get started. So our first speaker is Hyung-Rak Jo, who's speaking on cryptographic hash functions based on arc-transitive graphs.
Thank you for the organizers giving us the opportunity. I'm Hyung-Rak Jo, and this research is co-work with Shohei Satake. For the beginning, we introduce a cryptographic hash function. A cryptographic hash function is a fundamental primitive in a variety of fields in cryptography. A hash function is to map a text of arbitrary size to fixed size values. When constructing a hash function, it requires some conditions with computational infeasibility. First one is one-wayness, which means that for a given hash value, it is hard to find its preimage. Secondly, it is hard to compute the colliding hash value, which has distinct preimages. We call it collision resistance. For a given text, if it is hard to compute the colliding preimage, then we call it strong collision resistance or second preimage resistance. These hashing processes should be computationally efficient and also distribute hash values in a space uniformly. We hope to construct a hash function from a graph, which security mostly relies on the hardness of finding a path assigned from the given message. For an example, we consider it on a cubic graph, which is 3 regular graphs. Each vertex has 3 labels, and we assume that we take a message of L length of bits, and we also fix the initial vertex. Now we have a proper mapping from a message to the routed edge. Then we work on a given graph as, so the first bit is 1, and the second one is 1 and 0, and so on. Then finally we reach the terminal vertex. It became a hash value of a given message. There are many trials to construct a graph or group-based hash function. This is the timeline of those trials. The first suggestion is from Gemor in 1901. It hashes binary bits to 2 matrices G1 and G2 over prime field. These 2 matrices freely generate special linear group. The hash value is all products of the sequences consisting of G1 and G2. However, Gemor's scheme is broken by Gemor and Tirich using the lifting attack. They modify the generators and base fields as f2 to the n. And here x is a root of the defining polynomial of f2 to the n. In 2006, Charles Goren and Rotter suggest a hash function based on Ramanujan graph. There are 2 kinds of Ramanujan graphs. One is based on Lubotsky-Phillips-Sarnak graph and abbreviated as an LPS graph. And the other is based on a Peiger's Ramanujan graph, and which became an essential idea for supersingular isogeny Diffie-Hellman key exchange. Even though in recent many cryptanalytic attempts against the site are revealed, it is still a fact that the CDR hash function publish isogeny rate cryptography with variants of applications. And last year, Fuchs et al. Suggest the hash function based on the Markov triple. Unfortunately, most of the hash functions are known vulnerable by specific attacks, but these attacks are somehow in a heuristic way. If we change the generator G1 prime as G1 double prime, then we still don't know how to attack. Security of most of these suggestions relies on the hardness of assumptions to find passes in graphs. It reduces the group word problem in Cayley graph or direct graph. Finding a collision is equivalent to find a cycle in a given graph. So we want to guarantee the shortest cycle is large enough. Here we are trying to suggest the uses of a triplet and sextet graph, which also seen as arc-transitive graphs with large girth. We also consider the expansion property with the second largest eigenvalue, which guarantees that left-line mixing the hash value. It also concerns the expecting graph is not a bipartite graph. Additionally, it is possible to provide some useful properties as primitive. The scalability means we can control the size of output as demanded. And small modification property means that if there are any modification in a text, then it should affect its hash value. Concatenation property means, in other words, we say homomorphic hash function. It allows us to compute in parallel. And in recent, we also noticed that these homomorphic one-mating functions can be a mini-crypt primitive. Now we will prepare some nullities for suggesting a new hash function based on arc-transitive graph. So an S-arc of gamma is a sequence of S+1 numbers of vertices. Any two consecutive vertices in the sequence are adjacent, and with any repeated vertices being more than 2 steps apart. And an arc-transitive graph is the automorphism group acts transitively on S-arc, not on an S+1 arc. So in figure, it is a 3-arc transitive, and we call it the Patterson graph. And every directed 3 edges passed in the graph can be transformed into any other such path. And here is a fact. So the gamma is D+1 regular graph, which is the S-arc transitive. So it we have these figures, and it's a dialectic. It looks like dialectic path. And then there exists a distinct shunt automorphism, D numbers of the automorphism, D+1 automorphism, and we call it the shunt automorphism. And so these are the picture, and also the subgroup of this G, which is generated by this shunt automorphism, acts on set of the S-arc transitively. So now we propose a hash function from an S-arc transitive graph. We have a D+1 regular S-arc transitive graph. We first fix an S-arc V, and the end vertex V0 is the initial vertex. And there are D numbers of the shunt automorphisms, and we fully assign each theory text V to the shunt automorphism. And now we have a theory messages, and we work on a graph with a shunted S-arc by assigned automorphisms. First, X0 gives a shunt automorphism labeled by X0, and the initial vertex are sliding to the vertex V1, and which is the end vertex in next shunted S-arc. Successively, we compute the process. Here, for proper work, we should define the composite of automorphism and its inverse in order to back and forth to move vertex one by one. So the details are quite complicated, so we refer it to our paper. And last, we have a hash value as a terminal vertex. Now we discuss about the collision resistance. Here we claim that finding a collision, which is equivalent to finding a cycle in a given graph, gamma. So there is 2 conditions. And first one is there is no short cycle in gamma. And this can be verified if the shortest cycle in the graph is large enough. And also the second condition, the finding a cycle or a closed work containing the initial vertex V0 in gamma, which is computationally infeasible. So to guarantee this claim, we introduced a group word problem, and which must be infeasible. So to guarantee this second condition, so the following problem must be infeasible. Here, the G is a finite group with an identity, which is denoted by ID, and S is a generating set of G, and which is, we have D numbers of the generators. And the representation problem means there is for a given length L, find the word W, the length at most L, which is satisfying the word is product of this word is identity. And here the word is reduced. The balance problem means, so we have a given length of L and find two distinct words, W and W prime of length at most L, which is equal. And both are reduced. So by Biggs and Hoare's paper, one can construct a cycle from the solution of a representation in a balance problem. Now we want to compare the Cayley hash functions in a sense of the size of underlying groups, and which is corresponding balance and representation problem. So Cayley hash function means is there is a hash function from a Cayley graph, and the size of the group is only determined by the order of this group. And our proposing hash has there is a stabilizer of the vertex, any vertex in graph, and which is acting on a set of the arc transitively. And so in here, the n is the size of hash value space. Then Cayley hash, in a case of Cayley hashing, the hash value space is like exactly same as the cardinality of this group. But our proposed hash is a hash which is the cardinality of this given group over the cardinality of the stabilizer. So if you want the set some fix the size of the hash value space, then we should take the more larger group. Then we can make the more complexity. And we give a explicit families of arc-transitive graph. We give some notations, and PG1P is the projective line over finite field with infinity. And PGL is the projective general linear group. And so then we know the PGL acts sharply, transitively on the projective line. Thus, we can see there is a linear fractional transformation between PGL and the projective line. On projective line, we define a duet, which is an ordered pair, and triplet, which is an ordered pair, and we define the crossing ratio, which is the number of the list of 4 collinear points on projective line. So in figure, there are two sets of 4 points, x1 through x4 and x1 prime through x4 prime, and their crossing ratio are equal. So especially if it is -1, then we call them a harmonic conjugate. So now we want to define a triplet graph, and here we need some more notations. On projective line, so we define a quartet, which is an ordered pair of duets, and which are harmonic conjugates. So the crossing ratio of this is -1. And triplet is a set of 3 points. So the vertex of the triplet graph is or triplet. So we can choose the 3 subsets among the P+1 set. And the adjacency between the triplets is defined like this. And 2 triplets have common 2 points, and then its intersection and symmetric difference are also duets. And if they are harmonic conjugate, then they are adjacent. So we want to only consider the connected triplet graph, and so we consider only one component in containing the vertex T0. Then in fact, if we if we set up the P is 1 modulo 4, and which is a prime number, then triplet graph always has 2 isomorphic components. So we only select the one component containing this vertex in here. And the number of these vertices is approximately P to the third. And this TP is a 2 arc-transitive. So in figure, this is also the Peterson graph. And if we choose a P is equal to 5, then we have a 2 isomorphic components, but we only consider the one component of this containing this vertex T0. And as mentioned before, so by linear fractional transformation, we can describe the shunt automorphism as 2 matrices A and B like this. Oh, I'm sorry. Some malfunction. Okay, now we give a definition of sextet graph. So we remind the definition of quartet. So the duet, the pair of the duets are harmonic conjugates. And sextet means we have an unordered triple of the duets, and these 3 4-point set is our quartets. Then we this triple of duet is we define it sextet, and the vertices are sextets, and we assume the P is equal to 1 modulo 8. And this relation is a little bit tricky. So we consider the 2 sextets, X and Y, and these are adjacent if each duet is one side here in Y, fixed points of the involution of Q and R and S. And here Q, R, and S are all combination set of 2 duets in X, excluding the common duet. So we will give you some detailed explanation. So these sextets have a one common duet with each other. So in here, X0, sextet 0, we have X1 and X2, and here X1 and X2 is these common duet. And here X3, X4 is common, and 0 and 3 is the third one is common duet. And we consider we only consider this relation, adjacency relation. So from here, we consider all combination of 4 points without this duet, and X3 and X4 and X4, X5, X6. Then it is to Q, and this is a quartet. We already know because we started from the sextet 0, and which is already by definition quartet. But the other combination R and S is not quartet. So we want to find this kind of quartet by defining each involution, and we figure out the fixed point of this involution. And there is a new duets, and these are amazingly these are the consist of sextet. So in this way, we can here, and we fix here, and we find this process. Then we can find a sextet adjacency relation. And sextet graph. So in order to represent the shunt automorphism of sextet graph, we need some setup in general. So we suppose P is 1 modulo 16, and which is the prime power. I'm sorry, this is not the prime power. Here is P just a prime number. And sigma is a primitive 8th root of unity. And SP is the component of this sextet graph containing this initial vertex. And CD and shunt automorphism of SP, and then in PSL, so we have this shunt automorphism in projective special linear growth. And then the fact is the sextet graph is non-bipartite cubic 3 regular graph, and the numbers of these vertices are approximately p to the third, and SP is for Arc-Transitive. So if you propose the hash would have no short collision, which is derived from the information of girth, and n is the number of the vertices, and the girth of the triplet is bounded by this number. And for any cubic graph, the girth is equal to log n. And this is the conjecture for in the case of a sextet graph, and there exists a constant c. And so comparing to the other the other graphs, and the girth of choose Ramanujan graph has this form. The choose Ramanujan graph means there is a three regular version of the Lubovsky-Fields graph. And on the other hand, in sextet graphs, numerical results suggest that C is larger than this constant. And we also proved that triplet and sextet graph are families of expander with some constant smaller than 3. And we also show that two graphs are not a Cayley graph. So now we give out some possible attacks on purpose and performances. So the underlying group is of the group word, and gamma. So when we consider the triplet, and the group is generated by these A and B matrices, and which is equivalent to a projective special linear group. And also in the sextet case, also the sigma is a primitive of H root of unity, and the generating by this C and D, then it becomes projective special linear group. So possible attacks, we are dealing on shunt automorphism A, B, C, D in each case, for each case, and N is the size of hash value space. And generally, in a birthday attack and a low message attack can be applied, and which is operated in scale root N. And we also consider the subgroup attack, which is related to the balance problem in our case, and lifting attack, which is relating to the representation problem. And so for against this subgroup attack, there is some heuristic attack. And so collision length is like this, so which is represented by Muren and Saban. And for lifting attack, in the triplet graph, and the first suggestion of a general, their generating set, a generating number is very similar to A and B, for triplet graph. And but in general's case, we can apply the lifting attack from a special linear group to over finite field to integer set. And also we can use the Euclidean algorithm, but in our case, we don't know yet. And in sextet graph, so the lifting attack is, which is considering from solving norm equation of this LPS hash function, LPS graph, and which is represented in the quaternion algebra. And so we can randomly choose those variables in X and Y, or these two, and then we can apply the Conacher algorithm to this. Then we can find the factorization. But in sextet graph, we don't know how to do it. But actually, there is some information that about some norm equation in quaternion algebra with it. So about for sextet graph in Weiss, and the norm equation is like this. So for collision resistance, so for achieving 512 of this security, so the size of the hash value space should be 2 to the 10,024. Then we have to choose the P is approximately to 2 to the 342. And performances, so we set up the common prime, and it's like this, and basically it's satisfying the condition of each hash function, where we consider the triplet graphs and sextet graphs and choose hash function. So which is known, so we compare the performances. And so prime number P is, we choose this one, and we randomly sample the 300 text in length L, which is 10 to the 10,000 bit. And we hashing for text of the 10,000 bit, the average time of triplet is like this, which is most fastest, and sextet is next, and 2 is slowest. So now we summarize our work, and we propose a new hash function based on Arc-Transitive graphs and explicitly a triplet and sextet graphs, which are expanded with a large curve, and which is also a higher performance than a choose hash function. And the predictable attacks are all remediable, and which is related to balance and representation problem. And now we have some open problems. One is confirming the conjecture of the girth of a sextet graph, and also the further security analysis required. Yeah, that's all.
Okay, thank you very much. Thank you to our speaker. So it's a very nice talk. So would anybody like to ask any questions? We can take questions both from Zoom and from the audience here. The audience here would use the mic. What's that? Oh, and there's a mic in the middle, yeah. Anyone have a question? Do we have any questions on Zoom? If we have questions on Zoom, we can unmute. Okay, well, I have a quick question. I'm curious how difficult you think it might be to come up with more explicit examples.
Oh, yes. So we also consider, we also search other examples, but it is hard to find which has also the logic curve. So it is one of the some big challenging problem in graph theory, and so this triplet graph and the sextet graph is actually, it is suggested in 1988 and in 1992. So, but we don't know the further examples yet. We have a slide with some other examples in our paper, but which is not enough to construct a hash function for now. So we don't know yet the other examples, which has logic curve.
Okay, great, thank you. So let's thank our speaker again.
Thank you.